No record, but if you've got questions or if you can, you know, if you're off-site, you can email me or you can text Cole Garrett, he's got his phone, or you can Snapchat you. Who else wants to admit that they're here so people could text you?
I'm here. I'm here.
All the people that say hi are here. One person gave us a gold star and said that it's actually working. So we're up and going.
Yeah. Is this actually being recorded?
Yeah. It's being recorded at the same time. And we're going to see if we can keep going here with some Ch17 background stuff. So those of you watching online live, we'll be going here in just a minute. Those of you here in class or in the actual room, please realize that they can hear you online at the same time too. I sent out the link, yeah. And those of you that are watching online, you're more than welcome to send any questions once again by email to me or by text message to Cole, or you can text. Who else will take text message questions? Wally will take text message questions if you know who Wally is. Alexis Guzman will take text messages, and then of course you can just email me too, and I'll have my email up at the same time. And I'll probably be zooming in and out on this piece of paper as we go, and I have a bunch of stuff to go over. So here we go, folks. You guys that are here in the room, what I'd recommend is having a lot of paper out. I'm going to go through a background of I've got about 16 pages prepared of large letter notes for all kinds of background things for Chapter 17. We start way back at chapters long ago, and then we go all the way up until titrations. And hopefully I can build kind of a lot of the background knowledge that you need for that material. And then you can run with it from there. And then I'm going to end with about a half an hour. So it's probably going to take about 45 minutes for that background. So if you've got to leave or go, if you're live here, absolutely fine. Come and go as you want. You guys online, obviously, you can leave and I'll never even know that you left. And obviously not offended at all if you have to go or something like that. So you people here in class or in the room, live people, pieces of paper, and then you obviously can just raise your hand or just speak up and ask a question at any time. And I'll probably repeat your question so the people online can hear it at the same time too. So, yeah.
When is that chapter 15 through 17 test?
After the chapter 17 test.
So
Her question was, when is the chapter 15 through 17 test? And so after this week, we'll spend a day or two reviewing KSP next week. Then we'll take the chapter 17 test. That's probably about Wednesday or Thursday next week. Then we'll take, we'll probably start chapter 19 just a little bit, and then we'll have probably a day of review, and we'll do the large chapter 15 through 17 test. So it's probably 2 weeks away if you're looking time frame wise. Yeah.
When do you think we'll be done reviewing?
When do you think we'll be done reviewing like the online version right now? I don't plan to be done until 7 o'clock. So if you have to go sooner, don't feel bad. Go ahead, come and go as you please. Of course, the schedule all depends on how many snow days we get as well, and we're all planning on several of those in the near future. Okay, so here we go, background knowledge stuff. Starting right here, back with the basics. You got to be good at the molarity triangle. And remember, molarity is equal to moles divided by liters. And you got to be able to solve for moles almost all the time. So plug your molarity in and note that the units for molarity are a mole per liter. Or your book or the AP exam loves to write them as moles times liters to the -1. And then multiply that by the liters. And a tricky thing for some people is remembering that it has to be in liters, because they always give you something like 53 milliliters and say multiply it. And remember, that's always 3 to the left. So 0.053 would be, the number of liters. Okay? You guys that are in attendance here, how many people fist to 5 are pretty good at the molarity triangle? Do you want me to spend more time on that? That it's just moles Molarity divided by liters. You guys out in anywhere land?
No, we do not anymore.
The anywhere land people emailed me and said that they can't hear me. I wonder if I could turn the microphone up. Let me try this. Microphone boost. There, I boosted the microphone. I wonder if that'll help. I'm not sure. Okay, now I'm trying more sound. Alright, some people say they can see me but can't hear me. I turn the microphone up some more. We'll see if that helps. If that doesn't work, then maybe I'll unplug the microphone and maybe it'll work more. So first is molarity triangle. Second thing, you got to be able to know how to do mole to molar ratios. Okay, Sophie wants a shout out because she emailed in and said she can hear now. Okay, shout out to Sophie. Congratulations. Thank you very much for the email. So mole to molar ratios. So you got to be able to do my ratios like this. Know that this is a 2-to-1 ratio. And then the tricky things you got to be able to do with this is that if there's 5 moles of X and 5 moles of Y, which one limits the reaction? How do you know? How do you figure it out? A quick, easy, dirty way is to just take and divide it by the coefficient, and then whichever one ends up being smaller, of course, is the one that's going to limit. And so the one that limits this one is going to be this guy right here because it's going to be the smallest. Sorry, I got my papers mixed up there for just a second. And this would be the excess reagent, and you should be pretty quick at telling which one's going to limit and which one's going to produce whatever it is. So if it's going to produce XY over here, and we say how many moles would it produce over here, we do 5 divided by 2 times 1, so it produce 2.5 moles of this stuff over here. How many people are okay with this mole to molar ratio stuff? Where this becomes a little bit more tricky lots of times is when we do something like this. A plus B goes to C plus D, and then we say there's this many moles of A, this many moles of B, and then we do an ice table like this. And most of the time in what we're doing, it's a 1-to-1 ratio, so it's really easy to figure it out. You can say, well, it's the smaller one that limits. So the one that's smaller here would be the 0.0053, and so we'd say that would totally be used up. And we'd also lose a 1-to-1 ratio here, so we'd lose 0.0053 here. We'd end up with 0 here, and this would be 0.002, I think. Did I do my math right there?
Yes.
And then this, of course, would create, since it's a 1-to-1 ratio, 0.0053 here, and create 0.0053, and you've seen this, that you'd end up with some here, and some here. And then we'll get to it in just a second, but we could write a K expression from this. There would be products divided by reactants to the powers of the coefficients. So questions about this stuff, writing an ice table like this, and using the moles right here to determine how much products there are or how much reactants are left over. Yeah?
So you only divide the moles by the coefficients to find the limiter? Like, once you divide it, you don't use the quotient as the actual moles in the problem?
Yeah, so her question is, once you divide the number of moles by the coefficient, you don't really use that anymore, and that's true. The only reason you do this is to figure out which one the limiter is. Now, if they ask you a question, once you know what the limiter is, and then they ask you a question like how much XY is made, now you take 5 moles of X and make your ratio between X and XY right here, and that would be a 2X to 1 XY ratio. So yes, you do use this coefficient here again, but I always call it like the quick and easy way to just figure out if the question is only which one limits, then divide by the coefficient and you know right away. But if they ask you more questions, now you need to use these coefficients to figure that out. Did that answer your question? Okay. So that's mole to molar ratios. You got to be pretty good at that kind of stuff, and be okay with with recognizing and figuring out how many things are left in each spot. Okay, next page. Let's see. Sorry, just got my pages a little bit mixed up here. I just want to make sure to cover the background stuff first. Well, I guess it goes kind of into this. I kind of said that, now from this we could find a K expression, so what the heck is K? So let's go back to that. And if we had a reaction like this one right here, x plus y goes to xy, and we wanted to know, well, what is the equilibrium constant expression for that? We would take the products and divide it by the reactants to the power of the coefficient. And if there were a 3 here in front of the y, of course we'd have to raise this to the 3rd power. Give me a fist of 5 if you remember this. Products divided by reactants to the power of the coefficient. This is also known as the law of mass action. Law of mass action, okay? So if it's an acid or a base, though, now we give this K a special name. So here's an example of this. HF reacts with water to make H3O plus and F minus. And instead of just calling it K, now since this is an acid, we put a little A down below it. And we put the products on the top, H3O plus in brackets, times F minus to the 1st power, because they both have 1s in front of them, and then divide it by HF over here. And who remembers why we don't include water in this expression?
It's not aqueous.
Yeah, because it's a pure liquid, right? Remember, pure liquids and pure solids never end up in the never end up in an equilibrium constant expression. And remember, the reason we call it A is because it's an acid. If it was a base, we'd call it base. So here's my other question too. In this equilibrium, many times they ask questions about what is going to be the result of this equilibrium. And usually there is a particular ion we're interested in. For example, if they ask about the pH of the solution, which thing would we want to find if they asked what's the pH of this equilibrium? Yeah, the thing we'd be interested in then is the H3O plus. How do I know that? Well, because I know how to calculate pH, okay? Which leads to the next thing that you have to be kind of good at. Once you can write this K expression, you've got to remember this pH square, or this pH box. And one of the things that sometimes confuses people is that H plus and H3O plus is used interchangeably, and they mean the same thing. And so you have to be able to move pretty easily between these without using the pH box that's on just our nice periodic table that you use a lot. Just for people that are either watching or in the room, do you want me to go through and do some sample calculations with these, or are you good with those and just get on with the rest of the stuff and don't spend much time on pH, POH calculations?
Yeah, we're good. We're good.
Good with that kind of stuff? Okay. The other relationship that is really similar to this, oh yes, question.
Can you do one where you do pKa to pH?
Oh, very good. Thank you for asking that. She asked, can you do one with Ka, pKa? Because just the same as the pH relationship, we can also look at the relationship between Ka, pKa, Kb, and pKb. And the boxes, I purposely did them next to each other because they're actually the same relationships. They're these P relationships right here. And so Ka and Kb are related as Ka times Kb is equal to 1 times 10 to the negative 14th, just like H plus and OH minus are. And if I'm going from Kb to pKb, it's the negative logarithm of the Kb. And if I'm going from Ka to pKa, it's the negative log of the Ka. And of course the P's are addable just like the pH and the pOH. So pKb plus pKa is equal to 14. So to answer your question, if I had a Ka equal to, I'll make it real easy so you can do it without a calculator. 1 times 10 to the negative fifth, what is the pKa, what's the pKb, and what is the Kb? I'll give you about 30 seconds, see if you can answer all of those really quick. So the first one for the Ka right here, the pKa would be equal to the negative logarithm of 1 times 10 to the negative fifth, which would be 5, because you're just taking the negative log of this thing right here. And then I know that the pKa plus the pKb is equal to 14, so that means that the pKb would be equal to 14 minus 5, or 9. And then the Kb, of course, would be 10 to the x, or 10 to the negative ninth, right here, 10 to the negative pKb. So I could also write that as 1e negative 9, or I could write it as 1 times 10 to the negative ninth. Does that answer your question good enough with the Ka-Kb relationship square? I don't know if it's really called a square or not, but is that good?
Yeah.
Is that good? Okay. So good you asked that question, because you need to be able to move throughout this square just like you have to be able to move throughout this square. Okay, next part. Next part, you need to be good at recognizing things. So we're going to move away from the mathematics for just about 4 pages now and talk about recognizing strong, weak, and non-electrolytes. Okay? The strong ones we learned way back in chapter 4. The strong acids are Hyber, Pickle, High, Hono, Piccolo, 3HClO4, and H2SO4. I had somebody just the other day that, forgot that this was HClO3 and HClO4. So, you simply got to memorize those. Hyperhickel, high, honohickel, H2SO4. The strong bases, remember, are lithium, sodium, potassium, rubidium, cesium, and then calcium. Don't forget there's a 2 there. Strontium and barium hydroxide. And, you got to remember those from your periodic table here and know that it's lithium, sodium, potassium, rubidium, cesium, calcium, strontium, barium, but it's the hydroxides tacked onto those. Okay? Those are the strong bases, and, you remember those because they form a B on the periodic table like that. Remember, they've got the OHs stuck on. So those are the strongs, strong acids and strong bases. Now what about salts? Well, you can pretty much say is any time that there is a salt that is soluble in water, it is a strong electrolyte. And to know whether or not a salt is soluble in water, you got to know your solubility rules. So you remember the CAN rule for chlorates, acetates, and nitrates. Okay, those can always be soluble, can always be soluble. And then you know that the chlorides, bromides, and iodides are all soluble. Anything that contains these at any time, except 3 of them happen to not be soluble, and those are mercury, silver, and lead. Mercury, silver, and lead. Okay? And then, let's see, besides those guys, there's the sulfate rule, and that means all sulfates are soluble except for Fabs. Okay, and remember that's lead, mercury, silver, once again, these same 3 guys, and then barium and strontium. Those are insoluble. These are the insoluble ones. And then lastly, the most forgotten rule, and probably the most important one, is that all group 1 ions are soluble, along with ammonia, NH4+. If it's got ammonia in it, always soluble. If it's got anything else from group 1, lithium, sodium, potassium, rubidium, or cesium, always soluble. Now there's some other really weird little rules in there, but these are the main ones, and if you know these, you're good. And they are considered a strong electrolyte. They completely dissociate, divorce, split up, ionize, make charged things in solution. They do all of these things when they're dissolved in water. Any questions about the strongs? Now the confusion comes for a lot of people in, which things are weak. Well, everything else is weak. Everything else. Okay, weak or non. Weak or non. Okay, one of those two. It's either a weak or a non. So, more about weak particles, especially acid and base weak particles, because those are the ones that usually confuse people the most. So let's start with the hardest part first, the bases. Which ones are the weak bases? Well, I've got some up on the screen to your right that maybe you've never seen before. The most popular one is something called ammonia, NH3 right here. And you'll notice that it is a good proton acceptor. And remember, a proton is an H+, because it has this unshared pair of electrons right here. Hydroxide fixes that. This is actually a strong base, but you can see that it's a base because it's got a couple of those unshared pairs of electrons. That's good at accepting electrons. You can see a couple other ones on the screen to your right, like hydrogen sulfide ion. That's a good that's a good weak base because it's got some unshared pairs of electrons on the sulfur, which make it be a good acceptor. Okay, lots of times you get these weak bases from anions, like things like carbonate, or things like the hydrogen sulfide ion. They're good weak bases. They're things that are good acceptors. And, the number one reason that makes them weak is they're not on the list of the strongs. They're not on this list, okay? If they're a hydroxide and they're not on this list, they're probably insoluble, number one, and number two, they're definitely not a strong base. So, they're not. Just so you memorize the strongs and everything else is weak. Acids-wise, which things are weak acids? Well, if they start with an H, you can make a good guess that it's probably a weak acid, okay? So if it's like HCN, or HF, or HNO2, or H2SO3, these are not ones you memorized. So that means that they're a weak acid, which means they only partially dissociate, partially break up. Give me a fist of 5 on weak bases and weak acids. Do you want me to talk more about those, or are you good? All right. So basically, since it's a base, bases. These are the strongs. Anything else weak? These are the strongs. Anything else weak? Anything that's not soluble, weak. Anything that's not soluble, weak. Yeah, there's a good question. Go ahead.
So to tell if it's a weak base, you can do Lewis dot structures, and then the ones with like unpaired electrons are the ones that are like weak bases.
I can't say always, but I can say. So her question is. Her question was. You can draw the Lewis dot structure, and then if you draw the Lewis dot structure, if it has unpaired electrons, that means it's a weak base. That doesn't necessarily always mean that. It's just a good indicator. And you can see, if it doesn't have any unpaired electrons, then it probably doesn't have a very good chance of being a weak base, because it probably doesn't have a very good chance of being a weak base because there's no way it can accept electrons. So I can't say always, but it's a good way to tell. And if you look to the ones on the right, over on the screen to the right, you'll notice they all have unshared pairs of electrons. Does that answer your question at all, or probably not as good as you want it to answer? Yep, another question.
Well, but if only strong bases are the ones on that list, then you need to draw the Lewis dot structure, because, like, if it's only the strong bases that are in that list, like, you have your answer. If it's not on there, then it's weak, right?
That's what I think. Yeah, she said if it's not, if it's not on the strongs list, then, well, what is it? Well, it's weak. Okay, so, if it's not on here and they tell you it's a base, well, then it's definitely a weak. If it's not on this list and they tell you it's an acid, it's definitely a weak. If it's not soluble, then, well, it's definitely going to be interesting to you, but it's, it's definitely a weak thing. A weak thing. Okay, so now going on with more recognition things. Acid, base, conjugate acid, conjugate base. Acid, base, conjugate acid, conjugate base. Okay? Here's an acid, HNO2. What is its conjugate base? Well, the definition of conjugate base is what's left over after the acid has released its proton. The proton is the H. Once it's gone, what's left? NO2 with a -1 charge. So here's the acid, here's its conjugate base. You try this one, HClO2. What's the conjugate base? Get rid of the hydrogen, it would be ClO2 minus, right? Okay, try this one, HC2H3O2. What's the conjugate base? Get rid of the hydrogen, C2H3O2 minus 1, right? That's the conjugate base. Here's a weak a weak base. What would be its conjugate acid? Now, a conjugate acid is the definition of what is created after a base has accepted its proton. Okay, it gained a proton, so it would be NH4, and remember it's got to go up in charge, because hydrogens, remember, have a +1 charge, okay? How about OH minus? What would be its conjugate acid? So after it gained a proton, what would it be like? It would be HOH, right? With no charge, because it went up in charge. How about CO3 2 minus? What would it be after, what would be its conjugate acid? Put an H on the front and raise it 1 charge. It's no longer 2 minus, it would just be minus. Hey, take this one now, and what would be its conjugate acid if this acted basic? H2CO3, right? So this is actually a diprotic acid that loses a hydrogen, and then it loses another hydrogen if you're going this way. If you're going this way, this is a base that gains a hydrogen, and then this is a base that gains a hydrogen this way. Do you see how that can work, both backwards and forwards? And you can call them conjugate acid and conjugate base depending on which side you start from. If you start from here, here's the acid, conjugate base, conjugate base. If you start here, it's a base, here's the conjugate acid, here's the other conjugate acid. Okay? Any questions about conjugates? Yep.
So like bases don't necessarily have to have an H in them?
No. This guy right here that's a base doesn't have it. Her question was bases don't necessarily have to have an H. No, bases are good at getting H's. They don't have to have an H to start with at all. As a matter of fact, something like this, S2 minus, hey, it's a good conjugate, it's a good base. Because what would it look like once it got a hydrogen? HS minus. And this guy could be a decent base too. What would it look like if it got another hydrogen? H2S, okay? So, things that don't have H's can be good bases because they're good at getting hydrogens. Does that answer your question? Okay, so now being good at recognizing acids and bases and conjugate acids and bases allow you to answer this difficult question. If you have a salt and you dissolve it in water, will it act acidic, basic, or neutral? How do you know? Okay, first of all, what is a salt? That's the first question we have to answer. Well, a salt is created when two parents come together to create it. There's an acid parent and there's a base parent. When they come together, the H and the OH are going to form water, and then the cation from the base and the anion from the acid are going to join together, and this thing is called the salt. So you maybe have heard this before, an acid plus a base makes a salt and water. Makes a salt and water, okay? Here's the salt and here's the water. And then the salt had two parents. One parent for the cation came from a base, and the parent for the anion came from the acid. If you keep that straight, you're pretty golden, because then you can figure out where the salt came from. Okay? So here's a little bit more about that. The acid is the parent that gives the anion, acid, anion, acid, anion. Do you see that makes sense? AA. Base, cation, BC. They're both consonants. It's going to be the source of the cation. And then the salt right here is LiBr. Lithium from this and Br from here. Okay? Now, how will it act? How will it act? Well, if the parent is strong, if the parent of the salt piece is strong, it will do nothing. It has no affinity and doesn't want to get any H pluses or any OH minuses. So for example, this guy right here is made up of a strong, came from a strong base. It doesn't want to get OHs and look back like this, because remember, this wants to completely dissociate, divorce, be far apart anyway. This guy right here is the anion of a strong acid. It doesn't want to get any H's and go back and look like this, because this parent totally divorced, dissociated, ionized, whatever you want to call it. So this guy would be neutral in solution, because the lithium did nothing and the bromine did nothing in solution. Has no affinity, no want for H pluses or OH minuses. Question in the front, yes?
Both parents have to be strong?
No, that's a good question. She said both parents have to be strong. If only one parent is strong, that particular anion or cation will do nothing in solution. The other anion or cation, if it came from a weak, will do something. So let me go on to another example right here. Okay, if one of the parents is from a weak acid or base, now pay attention to it, because that's the thing that's going to act acidic, basic, or neutral. So for example, let's say that we had a base, NH4OH, and an acid like, maybe like HCl, okay? Now, when we create this right here, we're going to end up with NH4Cl, and then we're going to end up with the OH and the H together, okay? This, of course, is water, so we don't care. But now break this guy up. Where did the Cl minus come from? It's the anion, so it came from the acid. What kind of acid was it? It was a strong acid, right? So what will the chloride ion do in solution? Nothing. It will just spectate. The NH4, where did that come from? Well, it came from this base. Is it on my list of strong bases? No. So that means it must have come from a weak base. This guy is a weak base. And now pay attention. It wants to go back to look like this if it can, okay? It wants to go back to look like that if it can. And since it's a weak base right here, this guy right here will want to act acidic if it can. It wants to act the opposite of what its parent was. And writing the equation as this being acidic is probably the toughest thing that you have to be able to do. Let's do a bunch of examples like this and have you try some, okay? Let's take, well, I already did this one here at the top. Let's take this one, KNO2. I'll do this one together with you. Bust it up. K plus and NO2 minus. Now answer the question, where did K plus come from? What cation, therefore what base did K come from? His parent must have been KOH, right? This was a strong base. So what will it do in solution? Nothing. NO2, what parent or what acid did it come from? HNO2. Is that on your list of strong acids? No, it's not a strong acid, so pay attention. This guy is going to want to get to look like its parent if it can again. What does it have to do to get to look like the HNO2 parent? It needs to get a hydrogen, and things that get hydrogens are called bases. So this, KNO2, when dissolved in water, would act basic. Okay, I'll be quiet for a second. You try this one. NaNO3, acidic, basic, or neutral? Okay, Na, where did it come from? NaOH, strong base, will do nothing in solution. NO3, where did it come from? HNO3, strong acid, will do nothing in solution. How will this thing act? Neutral. It'll do nothing. Okay, fist of 5 on how you did on this one. 5, 4, 3, 2, or 1. Okay, try this one. K2CO3. Split it up. Is it going to act acidic, basic, or neutral? Alright, K plus is the cation, so the cation always comes from a base, so tack an OH on the front of it and ask, is it in my list of strong bases?
Yes.
The answer is yes, it is. So what will it do in solution? Nothing. Remember, if it comes from a strong, it'll do nothing. Okay? CO3 2 minus. Where did it come from? Something with an H on the front of it, right? Always tack an H onto the anion because the anion came from some acid. Is this a strong acid? No, it came from a weak acid, right? It came from a weak acid. Its parent was a weak acid. It wants to look like this if it can. What does it have to get to look like its HCO3 minus parent? Has to get a hydrogen to look like this, right? Therefore, we say it is a good proton acceptor, and we say that it is a base. So its parent was a weak acid, it will act basic. Fist to 5 on that one, how'd you do? 5, 4, 3, 2, or 1? Okay, try this tough one right here. Okay, this one might be a challenge for some people to split up, but you got to recognize that I've got this thing called bromine in here, and that's got a charge of -1. So there's my anion right there. This other fuzzy looking thing that I probably have no idea what its name is, that's some cation that, you know, I don't really care what its name is. I just know that it's got a positive charge. So let's start over here, because this is easy. Where did Br- come from? Came from HBr, right? What kind of thing was HBr? We got strong acid, so how it's going to act in solution? It'll do nothing, okay? This guy, always tack an OH onto the end of the cation. Where did that come from? Definitely a weak base. That's not on my list at all. So if it came from a weak base, how is it going to act? It's going to act acidic, and it's going to want to give away a proton if it can to look like its parent weak base. Fist to 5 on that one. That one was a tough one. If you did well on that one, you're going to do pretty good. Pretty good. Any more? You want me to do any more of those acid-base salt ones? We're going to put it together now. Yep.
What if they're both weak?
That's a really good question. What if they're both weak? Panic. Panic. Okay? Because that's a big problem. Because then you have to actually look at, you know, say it was like BRO minus, BRO2 minus or something like that, and you know that this one would act basic too. So now you got something acting basic and something acting acidic. You'd have to look at the Ka of this and the Kb of this, and it would be a war between the Ka and the Kb, and whichever one was a little bit stronger would probably win out. But pretty much just hope you never see that, and then you don't have to worry about it, and it probably won't show up. So you ask a really good question. You probably have to answer, unless you have a lot of data in from you, you probably have to answer, it will act some way, but I don't know for sure. How's that for a really bad answer? Okay, pretty bad. Now let's put it together. Let's put it together with equilibrium, okay? Now we've got a weak acid or base and a salt, we stick them all together in one spot. And this is where the panicking usually starts in chapter 17. So here we've got 0.1 molar KNO2. Okay, that's a salt if you can't recognize it. Got potassium in it and some nitrite. And then a 0.1 molar solution of HNO2. What's the equilibrium of interest? What's the pH of this thing? What's the equation if I add this Hickel to it? What's this equation if I add NaOH to it? I'm going to slide it up here and I'll try to fit most of it on this paper. We'll see. Okay, when you encounter a problem like this, always look for the thing that's weak. Always look for the thing that's weak, because it's the weak thing that you're interested in. It's the weak thing that you're interested in, okay? So, this guy right here, just tackle them left to right and see what you can do. This guy right here has potassium in it and some nitrate in it. It's got a positive metal in it, and it's got an NO2 minus in it. I guess you can ask yourself the question, is it an acid? It doesn't have an H in it. Probably not, right? Is it a base? Well, maybe, but is it a salt? Does it have a metal and a non-metal, or a metal and a polyatomic ion in it? Yeah, it does. It's got a metal, and it's got this weird polyatomic ion, NO2 minus in it, so it's probably a salt. If you're not sure, just kind of say, yeah, maybe it's a salt, maybe it's a base, I don't know. Look at the other thing. Look at the other thing. What's HNO2? That one you should be able to get right away. Acid, base, or salt? It's an acid. What kind of acid is it? It's a weak acid. So look for the weak thing for the equilibrium of interest, and when in doubt, react it with water. When in doubt, react it with water. So take your HNO2 and react it with water. And since it's an acid, it's going to want to donate a proton, and it's going to give us some H3O plus, and we're going to have some NO2 minus 1. Now, we want to know the pH of this thing, okay? That's the second thing. So you can go ahead and you can ice table it, because eventually we're going to have to find out the interesting ion in this equilibrium. If I wanted to know the pH, or was asked to find the pH, which thing would be interesting to me? The H3O plus would be the interesting thing. Now, I initially start with 0.1 molar of this, and I initially start with 0.1 molar of, 0.1 molar of this, I should have been pointing to, HNO2 right here. And I also start with 0.1 molar of KNO2. What is KNO2 going to do when I put it in water? Now you got to go back to your solubility rules. What do all potassium salts do in water? They dissociate, right? So I'm going to get some K plus, and I'm going to get some NO2 minus. By the way, what is K plus going to do in solution?
Nothing.
What's its parent? Where did K plus come from?
KOH.
Came from KOH. So what is it going to do in solution? Nothing. How about NO2 minus? What would that do in solution? Where did it come from? It came from HNO2. Is that a strong acid? No. So how is it going to act? It came from a weak acid, so it's going to act basic, right? So when it splits up like this, I'm going to have 0.1 molar K plus, and I'm going to have 0.1 molar NO2 minus. Ooh, look, I have some NO2 minus in this equilibrium of interest. So initially, I also have some 0.1 molar of this stuff right here from this salt that dissolved. Now, if you're a good recognizer, and that's what this all comes down to, some experience recognizing, you can see I now have an acid and its conjugate base in solution. What do you call a solution that has an acid and its conjugate base in it? You call it a buffer solution, right? A buffer. And you can solve buffer problems 2 or 3 different ways. You can go through and you can do the lose x, gain x, minus x, and you can set up the Ka equals and put x squared over the top, or x over the top, and ignore these x's and say they're small. Or you can solve them with the Harry-Hasselbalch equation. pH is equal to pKa plus the log of base over acid. This equation, remember, is on the yellow periodic table, and you can use it any time once you recognize that it's a buffer. There it is, right there. Right there, sorry. Right down there. There's the pH. Plus the log of base over acid. Okay? So, plugging and chugging this one in here, I'd have pH equal to the pKa, and I don't know what the Ka is here. Maybe it's listed on another page in here. But then plus the log of base. What's my concentration of base? 0.1 molar. What's my concentration of acid? 0.1 molar. Ooh, 0.1 divided by 0.1. 1. What's the log of 1? 0, right? Okay, so that means pH is equal to pKa. So if I know what the Ka is, I can take the negative log of it, and I've got the pH. Pretty cool stuff. Okay, so going back to this part up here, what happens if I have this solution now? This solution with KNO2 and HNO2, and I add some HCl. I've got KNO2 in there, and I've got some HNO2 in there. And I want to add some Hickel. Who will Hickel want to go and react with? Well, first of all, what is Hickel? It's an acid, right? What do acids usually want to react with? Bases. Is this a base? No, so it's not going to react with that. Is this a base?
Yeah.
Well, this is a salt, right? Didn't we say that? It's got some K plus in it, and it's got some NO2 minus in it. K plus we said would do nothing because its parent was a strong base. But what about NO2 minus? What is that? That's a base. So now the Hickel would react with the base, and we could write the equilibrium of interest as NO2 minus plus HCl, arrow, good acceptor of a proton. We get some HNO2 over here, and Cl minus. This is an equation of how a buffer buffs the addition of an acid to it. Now I'm going to ask you the opposite question. We've got this same solution, KNO2, HNO2. And now I'm going to add some NaOH to it. What is NaOH? Base, right? Who will the base want to react with over here? I'm not going to talk for 20 seconds. See if you can write the reaction of that base reacting with the thing that it's supposed to react with in the solution. Okay, hopefully you guessed that NaOH should react with the acid, and you had it react with the HNO2. And the complete molecular equation would be Na going together with NO2, and the H going together with the HOH. How many people did this? Fist of 5. How'd you do? 5, 4, 3, 2, or 1. Okay, now a lot of times what they won't want is this complete molecular equation. They'll want what's called the Ionic Equation, because the ions really tell you what's going on in here. The base completely breaks up, right? So the NAs are going to go away and spectate. The HNO2, that's got to stick together because it's a weak, and the water sticks together because it's a pure liquid. So you just write it as OH minus plus HNO2, arrow, and then you'd get the NO2 minus off alone by itself, and the HOH over here. That would be what's called the ionic or the net ionic equation, because you took out the sodiums from it. Okay, questions about the buffer type problem now with a weak acid and its conjugate base in there, or a weak base and its conjugate acid. Well, I'm pretty much done with the review, and we've got about 30 minutes left, and I'm going to work a buffer problem from 2002, the released exam, and then I'm going to work 3 titration problems from different years that use these concepts. I'm going to put them up on the screen to the right, and then if you want to log in, using your device as well and check my answers along the way, that would be absolutely wonderful. And you can check just to make sure that my math is good along the way. But I'm going to start with this particular buffer problem first. 2002 B number 1. And I've got it up here on the screen. Is this the 2002 B number 1? Yep, here we go. 2002. Oh, maybe it's 2002 regular. Oh, no, that's 2003. 2002, here we go. Yeah, this is 2002, Form B. That's what I'm going to use. I'll zoom it in just a tiny bit. Zoom. Zoom. And we'll talk about this particular buffer question. And like I said, does anybody have a computer handy? Want to log in and just look at the answers for us? There's a couple. You can probably triple task, huh?
Sure, why not?
Somebody else good with computers?
I can do it if you want.
Okay. I just want to go here. You can log into our page really quick, and then you can pull the answers to this up. And then you can check my math along the way to make sure that I don't screw too many things up. I'll just start working the problem while you're bringing it up. And like I said, this is probably going to take about a half an hour to work a bunch of these problems, but go ahead and interrupt me along the way and ask questions, and you can see how a bunch of old AP questions are done. What usually happens is the first question on an AP exam in the free response part, as you can see right here, it's called Section 2, is always a Chapter 17 problem. It always has something to do with titrations, with buffers, with KSP. And you can see there's no difference in 2002. So it says first, lactic acid, monoprotic acid that dissociates in aqueous solution is represented above. It's 1.66% dissociated in 0.5 molar this. For parts A through D, assume the temperature remains at 298. Now that's important because at 298, which is also 25 degrees Celsius, this is where Ka times Kb is equal to 1 times 10 to the negative 14, and also where pH plus pOH is equal to 14. And if you change the temperature, those equations don't hold true. That's why they give you that information of what the temperature is. No other reason. So first of all, letter A, write the expression for the dissociation constant for lactic acid. So Ka. You want to try it? See if you can do part A of a actual AP test question. The first question is always easy. Get the full point. So there's my products divided by my reactants to the power of the coefficient. I think that's all they wanted. Okay? Fist to 5. How'd you do? 5, 4, 3, 2, or 1. Did you get the whole point?
We have to calculate its value.
Oh, I got to calculate the value. Oh my gosh, now they made it tough right away. Okay, I wrote the expression. Okay, now I didn't even read the hard part. So let's see, it tells us that initially the concentration is 0.5 molar. So there's my initial concentration. Initially there's none of this and none of this. It also tells us that it is 1.66% dissociated. So 1.66% is equal to my H plus ion concentration at equilibrium divided by the concentration of the acid originally. Okay, that's the original or initial concentration times 100%. So I know this guy right here is 0.5, and now the only thing that I don't know is the H plus right here. So take my 1.66 times my 0.5. I'll multiply both sides of the reaction by 0.5. 0.5s cancel out. I'll divide both sides by 100, so my 100% goes away right there. And, well, now I gotta run the calculator because I don't have the answers. Do you guys know what that turns out to be for H plus, or doesn't it give that intermediate answer along the way?
You know, just what's the password for the test? Because I think it's different than for the textbook. Exam? Oh, okay. Nice.
So I got H plus to equal 0.0083.
Yep.
Okay, so that's my equilibrium, 0.0083. And if this is 0.0083, what does this have to be? 0.0083. And if that's what it ended up being, guess how much I gained over here if I started with none? 0.0083. And if I gain 0.0083, how much did I lose over here? 0.0083. And now I can do that subtraction. And I think it turns out to be pretty close to what it is, but it's like 0.4917 or something like that. And now I can take these numbers and plunk them into my Ka expression up here. So 0.0083 squared divided by 0.4917 right here. And now, did you find the answer key yet?
Yep.
What did the Ka end up being?
1.4 times 10 to the negative 4.
Okay, you can try it on your calculator, but I think that's what it ends up being for the Ka after you plunk those numbers all into this expression. Okay, that's part A. Now, part B, calculate the pH. It actually gets easier. What do I have to do to calculate the pH? What's interesting to me in here that I can use to calculate the pH? This guy right here, right? So somebody on their calculator, negative log of 0.0083.
2.08.
2 point what? 08? 2.8 or 2.08?
2.08.
Okay, so there's my pH, 2.08. And now question 3, it starts to get interesting. It says that calculate the pH of a solution formed by dissolving 0.045 moles of solid sodium lactate. Uh-oh, what's that stuff? Okay, sodium C3H5O3. What kind of stuff would this be considered? I'll ask you, I'll give you 3 choices. Acid, base, or salt for this guy.
Salt.
It's a salt, right? It's a salt. Now comes the $1,000 question. Is it acidic, basic, or neutral? What's the Na going to do in solution? The Na would do nothing, right? Because it came from a strong base. How about the C3H5O3? Where did that come from? Came from a weak acid, so it's going to want to act the opposite. It will want to act basic, right? And you'll notice that this, oh, it's right here in my equilibrium. Ooh, okay. So it tells me now that in this particular instance, I have my 0.5 molar of this stuff, and then I dissolved 0.045 moles, 0.045 moles of this stuff into 250 milliliters, or 0.250 liters. Moles divided by liters gives me my concentration, 0.045 divided by 0.25. I think I did that right. It's 0.18 molar with respect to this stuff, and it's 0.5 molar with respect to this stuff. And now, if you're a good recognizer, you're jumping up and down, because guess what this solution has just become? It's a buffer solution, right? Because it's got a weak acid, and it's got its conjugate base in there. And what does it want us to find? pH, right? Now there's a couple of ways you can do this, okay? You can go ahead and say I lose X, gain X, gain X, and you can write that all out and set it equal to the Ka that we calculated up above. Or you could go straight to this equation, right? And this would be the base, and this would be the acid right here. There's a question in the front. I'm sorry. Go ahead.
Like for the buffers, does it always have to be like a weak acid with its conjugate base? Can it be a weak base with its conjugate acid?
She asked a really good question. She said the examples that I've used have been a weak acid and its conjugate base. Could it be a weak base and a conjugate acid? The answer is yes, it certainly could be. It just matters that it's a weak and it's salt. A weak thing, or a weak electrolyte, and it's salt. That's what makes the difference. So let's see, the pKa would be the negative logarithm of, what do we get for the Ka up above here? 1.4 e to the negative 4. So you have to do that, and then plus the log of 0.18 divided by 0.5, and then you get the pH. And is the answer to that one in there?
Yeah.
The pH?
3.41.
3.41. So see what happened to the pH once we added it? The pH here of just the regular acid was 2.08. When it became a buffer, what happened to the solution?
Got more basic.
Yeah, got more basic, because what did we add to it? Well, we added this thing, and you told me this thing was a base, right? Now let's see, letter D is a tough problem, and they said they weren't going to have problems like this on the AP exam anymore, so I don't want to do the whole thing, but I just want to show you what would happen. So in this one they say that there's HCl added to 100 milliliters of this. Oh no, maybe they would have this one on there. Calculate the molar concentration of C3H5O3 in the resulting solution. So they've got this HCl solution, and they're going to add it to HC3H5O3. What would it make? Well, really, you wouldn't want to write the equation for this one. Like I said, yeah, after I think about it a little bit more, I don't know if they put this in there very much, because really what this would be is, well, what kind of thing is HCl?
Strong.
And what's it going to do in solution?
Dissociate.
So you're going to get lots of this, right? And you're going to get some of this. And what's the Cl minus going to do in solution? Nothing. Okay. And the H plus would be a certain concentration, 100 milliliters, and there'd be a certain number of moles of that. And you could just keep this equation that you had right here. And what's happening now is there's a certain number of moles of this H plus initially in this ice table. So you'd have to put those moles right here. And then for this guy, it says 100 milliliters of the 0.5 molar solution, so you put those moles right here. And then it tells you there's none of this to start with. And then you'd have to go through and do the lose X, gain X, gain X, and ignore the X's and solve for this guy right here. A little bit tougher of a problem to recognize, hey, I added that strong acid, so that gives me this ion right here initially already. But maybe after you see it, you can be like, oh yeah, I guess I could know that this is going to break up and there's going to be some of that. Long problem? Long problem. Any other questions? Terrible problem? Terrible problem. Okay. Sorry, that was the one in 2002. Yeah.
How do you know the difference between a buffer problem and a titration problem?
and which one uses moles, and which one uses molarity?
Well, I'm glad you asked that question. She said, how do you tell the difference between a buffer problem and a titration problem? Because now I'm going to do a titration problem. And when do you use moles and when do you use molarity, she asked. And that's a really good question. So there's a short answer and a long answer. And the short answer is, to tell a titration problem, look to see that you recognize there's an acid and that there's a base and that they're combining together. That's the short answer. And when you see that, you are always safe using moles. You are always safe using moles. You don't always have to, but you'll always get it right if you do use moles. So when in doubt, convert to moles holds true when you recognize there's an acid and when you recognize that there's a base.
But then what's a buffer? Because I thought a buffer is acid and conjugate base.
Yeah, so then she said, what's a buffer? Because a buffer also has an acid and a base, but remember, it's a special kind of pair. It's an acid and its conjugate base, or a base and its conjugate acid. And they have to look like relatives to one another to be a buffer solution. In a titration, they're going to be like opposites of each other. They're going to be, ones that don't, you maybe seen before, but, you're like, well, they're, one's HCl and one is KOH. Well, they're not really relatives. Okay. So I always like to think of titration problems as two parts. The first part is the stoichiometry part, and in this part, convert to moles. Convert to moles and do the ice table. Okay? Do the acid and the base moles, find out how much is produced over here. This is why you got to know there's a limiting reagent. You got to find out how much of this is left, how much of this is left, how much of this is produced. Once you know how much of any of these things is left, now you can go on and do the second part and recognize, is there a weak acid and its conjugate base from the salt? Then it's a buffer problem. Is there no acid and no base left? Well, then it's just a salt, and you got to break the salt up and ask, is it going to act acidic, basic, or neutral? Is there only some base left and no acid, and there's some salt? Now you got to look at the base and see, is it weak, and does it have its conjugate acid over here in the salt? Well, then it's a buffer problem once again. Or is all the acid and all the base used up, and is the salt from a strong acid and a strong base? Well, then there's nothing to find the pH of anymore, because it's just strong acid, strong base, neutral solution. So, being a good recognizer when you're done with the stoichiometry is super duper important. And then when you hit the equilibrium part, it depends. If it's a buffer, you can use the Henry Hasselbalch. If it, is just a salt left and it's going to act acidic or basic, then you got to do an ice table again for the equilibrium part. Yep.
So to determine something's a salt, it's a metal with a nonmetal or a polyatomic anion.
Yeah, that's a good way to know it. You can also know that a salt came from the anion of an acid and the cation of a base.
Oh, okay.
Okay, so here's a titration problem. 2003, number 1. Okay, this one's actually fitting because we did a lab kind of like this the other day too that asked some kind of question like this. Okay, so here's aniline, a weak base, and it reacts with water according to the reaction represented above. Isn't it nice they tell you it's a weak base? You didn't even have to guess. They just told you a weak base. Then it said in letter A, write the equilibrium constant expression. Do I have to do that, or can you do that?
We don't
You do it.
Okay, let's go on to part B. It said a sample is dissolved in water to produce a 0.1 molar solution. The pH is 8.82. Calculate the equilibrium constant for this. So if I know the pH, guess what I can find? I can find the POH, right? And then from the POH, what really interesting ion could I find that's in this reaction right up above here? could find OH, right? So let's go ahead and let's do that. Let's try that on your calculator. Make sure you can do that. So 14 minus 8.82 equals 5.18. So that means the OH minus ion concentration is going to be 10 to the negative 5.18 on your calculator. So 10 to the x key, negative, and I get the OH minus ion concentration to be 6.6 e to the negative 6. Did anybody else get that? Nobody else did that? Did I do that wrong on my calculator? Is that okay? I think that's right. Okay, and now I'll go back and read the question. What do they want to know? KB, and remember that's going to be OH minus, I should have done A, I suppose, huh? C6H5NH3 plus divided by the C6H5NH2, right? I know this guy. Right here. Let me write the equation and you'll see that you know a lot more about it already. C6H5NH2 plus HOH double arrow C6H5NH3 positive plus OH minus ICE. What's the initial concentration of this guy? Read letter B. 0.1 molar, right? Don't care about this guy. None of this to start with. What did I just calculate right up here? So that's my equilibrium concentration of OH minus. Anytime you find the pH or the POH, it's always the equilibrium concentration of it. Okay? How is this guy and this guy related? So if I know this concentration, I'll know this one. Okay? And then I probably gained this much, right? 6.6 E negative 6 plus 6.6 E negative 6. So I had to lose 6.6 E negative 6, which means, wow, this is really small compared to this. It's probably going to end up being about 0.1 molar here again as well. And now I can put these into my equilibrium constant expression, right? And did you find the answers to this one? What was the KB? What did it turn out to be?
4.4 times 10 to the negative 10.
That sounds like possible, sure. Very good.
Thank you, I try.
Okay, so that's part B. Now part C. Here comes the titration part. This solution is titrated with 0.1 molar HCl. Calculate the pH of the solution when 5 mils of the acid has been added. Okay? So remember, titration problem, 2 parts. What's the first part?
Stoichiometry.
So we want the acid and the base, and we want to write the equation and ice table it, and always go to moles. Then we can decide on the equilibrium part after that. So we got to write the equation of HCl reacting with the base, and the base in this case is C6H5NH2 arrow. Hickel gives away a hydrogen, so you can write it wherever you want, but you know, C6H5NH3 positive. And then what's left over after the acid is released as proton is Cl minus. I'm going to leave a lot of space here for the ice table because I'm going to have to convert to moles for every one of these. And so it tells me that there's 0.1 molar HCl. And I need to multiply that by my liters, and my liters are 5 milliliters. 1, 2, 3.005 liters. Multiply those guys together, and what do I get? 0.0005? Too many zeros. Did I do that right? Okay. And then this guy right here, the aniline, it said, if you look back at B, it was a 0.1 molar solution as well, but it was 25 milliliters, so 0.025 liters. And multiply those guys together, and I think I have 0.0025. Is that right? Did I do my math right there?
Yeah.
Okay. And then there's none of this to start with, none of this to start with. Now, you've got to be good at the stoichiometry. Who's the limiter? Okay. HCl is going to be used up because it's the smallest one, right? So I lose 0.0005. I'll end up with none. I'll gain 0.0005. Oh, whoops. Not enough zeros there. I'll gain 0.0005 right here. I'll lose 0.0005 right here. Now I got to do a little subtraction. I believe I end up with 0.002. Is that true? And I have some of this. And I have some of this.
Do you think you could just go over how you wrote that equation again one more time? So you have the acid, which was from the question. Then you had to figure out which base it was, which is one of the things that's for the original equation.
So she asked a good question. They said, can you go over how you write this equation again? Okay. So I have my acid from question C, where it says the HCl is titrated with HCl. So I know that's going to be in the equation. And then it says the solution in part B. So I look back to part B and it says a sample of aniline is dissolved. What the heck is aniline? So now you look back up to the top of the problem and it says aniline, a weak base, right here, reacts with water according to the equation represented above. So I look at this equation right here and I see here's water. So what must be aniline? It's got to be this stuff, right?
Okay.
So now I got to take this stuff, a weak base right here, and I got to react that with the Hickel right here. And so I took the HCl, reacted it with that. I knew that this would give away a hydrogen, so that's why I wrote it with an extra hydrogen right here. And I also could look up at this top equation and look at this. This is a base right here that gained a hydrogen. So this is the conjugate acid that forms here. So I could use that to maybe help me write the equation as well. You can see how this and that thing are the same thing.
Yeah.
Okay. Did that answer your question good enough?
Yes.
Okay, now go back here and see that titration can take place in two parts. The stoichiometry, and now you're going to have some of this, some of this, some of this, some of this left. Now you're at equilibrium. You've got to recognize what it is. What's this? Acid, base, or salt? What kind of base? A weak base, okay? What's this?
Conjugate acid.
This is a conjugate acid of this weak base. How about this? Does this matter?
No.
Why not? Does not matter because it came from a strong acid. So I have a weak base and its conjugate acid. Oh, somebody asked about this earlier. What special name do you give a weak base and its conjugate acid? It's a buffer solution. So now at equilibrium, I have several choices of how I could figure out this pH. My personal preference is once you recognize it's a buffer solution, now jump right to this equation. Now, you might not have that equation memorized, and I don't think the expectation is that you do. So look on here. Where's the one that's got pKb in it? Right there. There's the POH thing. There's the, excuse me, log acid over base. I write it as acid over base like that. Okay, plug and chug these numbers now. Here's my acid, 0.0005, divided by my base, 0.002. Logarithm of that. Somebody with a fancy dancy calculator maybe can do that. And then the pKb is the negative log of the Kb, and we calculated the Kb up above. That was 4.4 e to the negative 10. I'm not making any sense. Log 4.4 e to the negative 10. Find that pKb, add it to this critter right here. Now, somebody's going to ask, and somebody maybe online's watching, how come I didn't divide these by liters? Because these are concentrations, remember. Concentration of acid and concentration by base. And remember, these are moles. Yes, somebody said it right here live. You know, I have 25 mils of this and 5 mils of this, so 0.03 liters. I'm going to divide this by 0.03, and I'm going to divide this by 0.03 liters. What's going to happen to both of those? They're going to cancel out. So when you recognize that it's a buffer solution and you're in moles, it's okay to just jump right into the Henry-Hasselbalch equation. You don't have to do the dividing right there. Okay, by the way, what happened to, well, did it ask for the pH or the pOH?
pH.
The pH, so what was the pH?
5.24.
5.24, so our pH from this equation should have ended up being about like 9 point something? 9 point, would that add up right? 9.75?
pOH is 8.76.
Uh-oh. Maybe I did something wrong.
No.
Oh, is that right?
Yeah.
8.76. Oh, yeah, that's right. Yeah, I thought it was be close to 9. That's close to 9. Yeah. Okay, it must be almost 7 o'clock. Yes, it is. Okay, do you want to do the last one, the titration of the equivalence point, and then call it good?
Yes, please.
Okay, so the last part says now calculate the pH at the equivalence point. So now you got to go back to your equation again, and we're at HCl and C6H5NH2 arrow C6H5NH3 posi plus Cl minus initial change end. What's true at the equivalence point?
Moles equals moles.
Moles equals moles. So how many moles of Hickles will be left, and how many moles of C6H5NH2 will be left at the equivalence point? If there's 10 moles of this and 10 moles of this to start with, how much is going to be left at the end?
0.
0 and 0. Okay, so we're going to have none and none of that left, right? Now, what we do know is that we have a sample of aniline that is 25 milliliters, and we know that it is a 0.1 molar solution, and we found the number of moles of this in the last problem. So I know that initially here I had 0.0025 moles of this, which means at the equivalence point I must have had 0.0025 moles of this. And they must have ended up being 0 and 0 right here. And I must have created 0.0025 moles of this. And at the end, I end up with 0.0025 moles of this stuff. Why am I focusing on this stuff? Why is that important? This is going to act as a conjugate acid, right? And the conjugate acid has some left. The chloride ion won't make any difference. So now, this time when you get to the equilibrium, remember the two parts, stoichiometry part, equilibrium part, you recognize that, hey, there's only this salt part left right here. And I'm going to have to go to an ice table to figure out what the pH is going to be. So, toughest of all problems, you have to take this now and make it act as an acid. Can you write that equation? C6H5NH3. When in doubt, react it with water. Arrow H3O plus C6H5 NH2. .0025 moles divided by my total number of liters. And since they're both 0.1 molar, I'm going to assume that I had 25 milliliters of this and 25 milliliters of this, so my total is 0.05 liters. So 0.05, did I do that right? Yeah. So I ran out of room here, I'm going to move my ice table down. 0.05 molar right here, change and end, okay? None, none, and none to start with. Lose X, gain X, gain X. 0.05 minus X, X and X. Okay, and now this is equal to the Ka of this thing, and that's equal to x squared over 0.05. I'm going to ignore this x and say that it's small. The water doesn't matter. The Ka I don't have, but I do have the Kb. So the Kb was 4.4 e to the negative 10th times the Ka is equal to 1 times 10 to the negative 14th. Divide both sides by 4.4 e to the negative 10th. I now have my Ka. I can do that on my calculator. 1 e negative 10 divided by 4.4 e to the... Oh, shoot. I did that wrong. And I end up with Kb equaling 2.27 times 10 to the negative 5th. Now multiply both sides by 0.05. Hope I don't push the wrong button here. I might. Now x squared is equal to 1.136 e to the negative 6th. Square root both sides. X is equal to
1.1 times 10 to the negative third.
1.1 times 10 to the negative third, and that's my H plus ion concentration. And now take the negative log of that. And I get 2.9.
Yep.
7. Wow. Oh, look at this last question. This is the funnest question on the whole thing. With pKa values for several indicators are given below. Which indicator is the most suitable for this titration? Here's the pH at the equivalence point. What do you want your indicator to do at a pH of about 3?
To change.
Change color. So which one would be the best to change color at 3?
First one.
Yeah, the erythrocyan. And that's the one that you choose. Thank you very much for coming tonight, folks. Thank you for tuning in. It was long, it was painful, it was powerful. If you want to do more, there's always more. 2005 number 1, 2002 number 1, 2007 number 1, they're all listed online. Lots of fantastic problems to do. Check the website out.